Okay, as I said before we stop, is that so because in order to replace this quantity to be just a Poisson bracket, you have to multiply this quantity by a sign. Yeah. So this is a little bit subtle here, but so which means that what we want to do is, this is a Hamiltonian constraint, we multiply a sign. Okay, but this is constraint anyway, so this constraint equals to 0 anyway. So if you multiply a sign, it is still a constraint. Yeah? So constraint equals to 0 minus constraint is still equals to 0 as well. And then which means that multiply and sign doesn't really programmatic in our program, and this is the quantity we are actually quantizing. This is what we are going to quantize. All right, so now you can safely replace this quantity to be the Poisson bracket. So now let me do the replacement. So this equals to 8 divided by kappa square beta epsilon ABC AB Poisson bracket CBR. Okay, so these well, to make all the index available here, this is x. Okay, this equals to sign E C0x. Okay, so this is the quantity we are going to quantize. Okay, so how to do the quantization? As I mentioned last time, is that well, as we did all the time for geometrical operators, so we have to first discretize this formula on the lattice, and then quantize the discretized formula. Okay, so now first we are going to just do the discretization. Okay. The goal of the discretization is that we are going to write this quantity, well, this sign, write the formula sign C0x to some C0v, to something with what we call C0v. So this is just the Hamiltonian. So here, this is Hamiltonian constraint, Euclidean term in the Hamiltonian constraint located at any point x. So these will be the discretized Euclidean Hamiltonian constraint located at one vertex v in the lattice. Okay. So now let's look at this vertex in the lattice. So this is 6-valent vertex v. Okay. And so here we are going to discretize two types of quantities. So one is this curvature. F is the curvature. So FAB equals to partial A AB minus AB A plus epsilon IJ K A J. Okay, so this is the SU2 curvature. SU2 curvature of H-scar connection. Okay, so now, so firstly, we need to consider discretization of this curvature. Okay, so the discretization, it involves the loop holonomy. So let's consider just the neighborhood of this this vertex. Okay, so this vertex, you come near this vertex. So adjacent to this vertex, there is many what we call blockhead. Yeah, blockhead are those small squares. Yeah, and which, so this is another vertex prime, and this is another vertex. So I mean, in neighboring this vertex, there are a few other vertices. So this is double prime, this is triple prime, let's say. Yeah. And then so near this vertex V, you can find 4 of other. You can find another 3 vertices, and then these another 3 vertices enclose a small square. Yeah, this small square is usually called a plaquette of the lattice. So these are just because you have cubic graph, you have cubic lattice and small faces, small squares in this cubic lattice. It's called plaquette. Yeah, plaquette. I forgot how to spell plaquette. Hopefully like this. Yeah. Correct me if I'm wrong. Okay. Anyway, so then on this plaquette, around this plaquette, you can find a. So here, let me orient the graph. So this is direction I, and this is. Let's assume all those edges. Well, these 2 edges are outgoing. So this is direction I. This is direction J. Okay, and this. So this the orientation is parallel to this edge, and this edge is parallel to that edge. Okay. And you can consider a loop holonomy. Let me change the color. You can consider a loop holonomy. Go around this plaquette. Yeah. So the orientation, yeah, it's a loop holonomy. So this is orientation of this loop. Yeah. And we know that along all the edges there are holonomies, right? And we define holonomies along all edges. That's our phase space. In order to define our phase space. So then you can connect those holonomies and to get a loop holonomy. Okay, and then this loop holonomy is actually relates to this curvature. And more precisely, so let me call this loop alpha ij, because this is a loop determined by the I and j direction. Yeah. And this plaquette is so whenever you have a I direction and j direction at a vertex, you get a plaquette. And then around this plaquette, you get this minimal loop. Well, this what usually we call alpha ij is the minimal loop. Well, you can imagine that this is really the minimal loop. Go around a square located at point B, at the vertex B. Okay, and the holonomy along this minimal loop, okay, has an expansion in the continuum limit. So it equals to 1 plus integral of Sij. So I call this plaquette, it is a 2 surface, it's a square. I call this plaquette Sij. So you can expand this holonomy if you shrink in terms of the edge length mu, in terms of the coordinate edge length mu, because I mean you can adapt this lattice to a coordinate, and then you can use your coordinate to measure the length of the edges. Yeah. So let's assume each edge has a coordinate length mu, and if you then this holonomy depends on mu, and if you expand in terms of mu, you will get this kind of expansion. The first leading order is just the 1 because mu goes to 0. Yeah. The holonomy is just identity. And the next to leading order is just the integration of the curvature on the plaquette plus higher order in mu. So this is of order mu square. This is of order mu square because this is a surface integral. So you don't have a feature of a loop holonomy is that you don't have any term linear to mu. If you expand, the next to leading order is just mu square. Okay. So well, this is a consequence of so-called a non-abelian Stokes theorem. Non-abelian Stokes theorem. Okay. Well, I'm not going to prove this non-abelian Stokes theorem, but to find the proof, you can just Google. If you Google Google non-abelian Stokes theorem, you will easily find the proof. But here I'm just going to illustrate why it can happen, why this formula can exist. Well, let's come to abelian Stokes theorem, the usual Stokes theorem. Let's consider just abelian group. Consider, so here this is obviously our gauge group is SU2, so it's a non-abelian group. Suppose you consider just electromagnetic field. The gauge group is just U1, is abelian gauge group, and you consider a U1 connection, U1 holonomy. So U1 loop holonomy is just this guy, right? And consider your electromagnetic vector potential, and you have a loop integral, have a closed circle integral. Well, your electromagnetic potential integrated along closed loop, and exponentiate. This is just a U1 holonomy, right? U1 holonomy. Okay, this is just a U1 loop holonomy. But you have Stokes theorem, so this just equals to your closed integral of this one form. It equals to a surface integral of two form of D. Okay, so this is along partial S. S is a plaquette. S is a plaquette, and partial S is just alpha, the boundary of plaquette, right? So if you have one form integrated along the boundary, it equals the two form. D of this one form integrate on the surface, but D of A, it is just a curvature, just the field strength. Okay, right? And then you expand. This is just 1 plus higher order, in mu 3. So this is the consequence of the this is just the abelian, so-called abelian Stokes theorem, or the usual Stokes theorem. So here this is some generalization of this. So that's why this is called a non-abelian Stokes theorem. But here the point is that this holonomy, this loop holonomy, it actually relates to the curvature. This is some discretization of the curvature. This is plaquette S, and well, so this partial S ij, this is just our loop alpha ij. Okay. So now for this is what I'm writing is just integrating of a two form. F is a two form, and it is a matrix value because well, here F is just well, because this holonomy is a matrix, it's a 2 by 2 matrix, so this F is also a 2 by 2 matrix. So this is this F is just Fi half, and I ignore AB because it's just a two form. Well, this one, if you write it in terms of coordinate, if you write it more explicitly, so this is just dxa dash dxb FAB. Okay, so if you write in terms of coordinate, but now suppose I adapt this coordinate x to the ij axis. Let's consider this this lattice. It is just adapt to the coordinate x, namely, so the I axis and the I axis, it is in the lattice is just the coordinate axis of xi, and j axis in the lattice is just the coordinate axis of xj. Okay, and mu is the coordinate length. All right. So now which means I can just consider, which means I can replace this AB index to be this IJ index. So then once I write this expression as a ordinary integral expression using the definition of integral in terms of differential form, what I get is this idxj fij. Okay, so here there's no sum in Ij because I consider here this is this plaquette is determined by I direction and J direction. So no sum. Okay, no sum. Okay, so these curvature term integrated along this bracket can be written approximately as the holonomy. Well, of course, up to a identity in the first term. Okay, so this is the first discretization of the curvature. Yeah, you can replace this curvature by column.
So here I have a question. Why do we call like FABI the SU2 curvature? Because we know like it's analogous to the EM field tensor, right? But is there a specific reason that it's called like that? Oh.
Well, yeah. you can call it field strength as well. It's no problem to call it field strength. So it is usually called, well, physicists call it field strength and mathematicians call it curvature. But it means really the same thing. It is curvature because if you consider the language of fiber bundle, so this SU2 connection, it is a connection on the principal fiber bundle, and this F corresponds to the curvature of the principal fiber bundle. So yeah, so this is, you can why depend on what we mean by why it's called curvature. So for mathematicians, this is just the name to call this guy defined from the connection is a curvature. And if your question is the motivation why mathematicians call that it's a curvature, it is because if you consider the frame bundle, I mean the bundle of the orthonormal basis over a manifold, and the the frame bundle has gauge group GLN, and then you define the curvature like this, yeah, over the connection on the frame bundle, yeah. Again, this is a connection on the principal fiber bundle, and you will get curvature on the principal fiber bundle defined in this way, and then that curvature corresponds to Riemann-Tensor. Relates to Riemann-Tensor, yeah, relates to real curvature of geometry. Yeah.
Okay, I see. Thank you.
Otherwise, you can just think this is a name, and it's perfectly fine if you don't call it curvature, you call it field strength. It's perfectly fine.
Yeah, okay.
All right. Any other question? All right. So okay, so this is the first building block in the Hamiltonian constraint, and then let's come to this second building block, the Poisson bracket between connection and volume. All right. So now this volume, we only need to consider any volume, any region R, such that this R is enclosed. This R encloses this X, such that X belongs to R. Okay. So now, so here this X will be the vertex V, and you can consider an arbitrary volume, which is around V. Okay. Right, arbitrary volume around V. So which means we can just replace this VR to be just the V, the volume at the vertex. Yeah. So we just need to replace VR to be V at V. Okay, so that, remember, and this V at V is just some kind of cube, right, enclosing the volume of a neighborhood, or the volume of a cube at the vertex V. Okay, so we do firstly this replacement, and secondly, what we can show is that this A so because we consider the coordinate adapt to the lattice, so here this C index can be replaced IJ index. So AI X and the volume V, it relates to this quantity. So the holonomy of EI and holonomy of EI inverse and then volume. Okay, so it relates to that. So why it is relates to that? So let me give you a proof. So let me just compute this guy. Okay. So let's see what it is. Holonomy EI inverse volume. Okay. So this equals to, so the holonomy only depend on the connection. Okay. So we can again use the chain rule of the Poisson bracket. That is d3x functional derivative h EI inverse delta x and then Poisson bracket I x dv. Okay, and this Poisson bracket is something you are going to relate, yeah, because this is the Poisson bracket here. So in the expression of Hamiltonian constraint. So what you only need to compute is this guy, right? And this guy is something you have computed already. So when we discuss about the holonomy flux algebra, so we have compute this guy already. Okay. So and now the so here you only need to be a little bit careful about there is an inverse. Okay. So there is an inverse. So you got overall minus sign d3x. Okay, so you get e dot. So you just apply the formula. So in our previous computation, so you got another integral. So this is so firstly you have a three-dimensional integral from above, and in this computation because your holonomy is a line integral, so you have another integral along the curve. It's called ds. Yes. And then you have h EI, and you have h. So here it is like, let me draw a picture. And this is your EI. Okay, and then you find so this is an intermediate point x of s, and then you are integrate along s. And then in EI, I think so these the first piece is E1, I call it E1. The second piece is called E2. So here you will, because you get an inverse, so you will get E2 first, and tau half I, and then H E1 inverse. Okay, and then multiply AI Okay, so this is your result. So so here this functional derivative, the result of this functional derivative is just give you this piece and this delta function e. Okay, so here is e dot a. This a is contract with this a, and also this overall minus sign coming from the inverse. Okay. All right. Also including this integral. Okay. So now again, you get a delta, and you can integrate out three-dimensional x minus ds and e dot I. I h e2 inverse one inverse. Well, I mean, I can put combine this tau half with this quantity, this Poisson bracket. So I can just replace this A by the matrix A, but I have to insert this Poisson bracket in the middle because it becomes a matrix. X S and right. Okay. All right. So now we see that well, as I mentioned, so I just put this tau half and this AAI together to get a matrix AA, and the matrix AA Poisson bracket with volume is a matrix, and then it is insert in the middle between two H's. All right. So now let's look at the continuum limit of this quantity. So because this Poisson bracket relates to this quantity only at the continuum limit, because we are just discretizing the Hamiltonian constraint. So we only need to verify that the resulting expression taking the continuum limit go back to the continuum formula. And here what we notice is that HE is just the 1 plus order mu. Okay, so which means I can somehow replace all those H's, just 1 plus order mu. And because this integral ds, this is order mu. This ds corresponding to order mu. So which means this formula, it is order mu. The leading order is linear to mu because you have an integral over ds. And then this h, if you keep this order mu, if you this h is different from 1 up to order mu, but these are correspond to higher orders. So this you plug in order mu and it just gives you order mu squared. So which means you can in the continuum limit you can just replace h by by 1. So under the continuum limit, it approximately equals to minus es along ei. So this along ei e dot ai ax volume. Okay, and now as I said that those ei, I will choose the coordinate system such that the coordinate will be along the I direction, J direction in the lattice. Okay, so then in that case, in this coordinate, I will let E dot AI. This E dot AI is just a tangent vector along the edge. Yeah, so then this E dot AI equals to partial xi. Okay. So just the coordinate basis. So the tangent vector of the coordinate edge of the lattice edge is considered just coordinate basis, and then this formula gets a little bit simpler. Xi AI x. Okay. Then of course, well, these I better write as equal plus order mu square, and again this is plus order mu square. So all these formula, all these relations are defined upon continuum limit. Okay, so you see that as I promised, this quantity holonomy inverse Poisson bracket with volume in the continuum limit just give you the Poisson bracket between A and B integrated along the edge. Yeah, integrated along the coordinate axis. Okay, so now we get the second relation how to deal with the second building block of this Poisson bracket. Okay, so now we can plug in this this relation. Okay, so now let's again look at the neighborhood of the vertex. So this vertex V. Okay, and now let's according to our notation about orientation, let's consider all the orientations are outgoing from the vertex, and so firstly, this is 1 plus and 2 plus 3 plus direction, okay, and this is 3 minus, this is 2 minus 1 minus direction. Okay, so now so 1 plus 2 plus 3 plus you can build using these three edges. You can actually build a cube, because it will get another vertex, so it will be v plus 2 hat, right? And then here this is another vertex, and this is another vertex, and here I don't know how to draw. Let's draw it here. This is another vertex. Okay, and now here you can get a cube. Well, I better choose a different color. That's maybe it's going to be more illuminating. Okay, so these three edges, 1 plus, 2 plus, 3 plus, these three edges determines a cube. All right. So now let's consider integral of, let's just draw a cube to illustrate this cube. Yeah. And to integrate these Hamiltonian constraint along this in this cube. So dx1, dx2, dx3. So our coordinate. So as I said, our coordinate already adapt to the lattice. So the 1 plus is a coordinate axis, and 2 plus, 3 plus they are also coordinate axis. Determinant E C0. Okay, so this equals to plug in the formula, continuum formula. X1 dx2 dx3 epsilon. So since our coordinate axis is just ijk, so I replace previous ABC in terms of actual coordinate axis, ijk, coordinate indices, ijk, fij. So here you get you have repeat index also sum. So you can view the previous ABC, they are abstract index, and here ijk, they are actual coordinate index. Okay. Well, you can safely replace these. You can add a 1 here. Trace. You can replace this f by 1 plus f. J. Closing bracket ak bv. Okay. Well, the reason is that well, you are free to put a 1 because this ij is anti-symmetrized. This is ij is anti-symmetric. Yeah. So if you put 1 here and here, this ij is anti-symmetric, you sum over I and j, you just get 0. Yeah. So this 1 has no contribution because it is anti-symmetrized with respect to I and j. So you are free to put a 1. So here this f will become 1 plus f. You can replace by holonomial. Okay. All right. So now you can consider. So here in this formula, you can, for example, you can consider this dx1, dx2 integral give you an integral on the plaquette, and then this integral of the plaquette integrating this f. Okay, integrating this f. And then the dx3, it is a line integral integrating this Poisson bracket. Okay. So which means you split up this 3-dimensional integral into a surface integral, say dx1, dx2, and the last integral dx3, which integrating this Poisson bracket. So here you see you have 1-dimensional integral integrating the Poisson bracket, and you have two-dimensional integral integrating this curvature. Okay, and the two-dimensional integral integrating the curvature you can replace by holonomy, and one-dimensional integral integrating the Poisson bracket you can replace to holonomy Poisson bracket with volume. Okay, and also you see, and these always depend on the choices. These always depend on choices. So in case here you have sum over ijk. Maybe I write it more explicitly. Okay, so let me write one more step. Beta, so this dx1, dx2, dx3, dx3. And this epsilon ijk you can expand in components. So epsilon, let's say 1, 2, 3. You get trace f1, 2. Poisson bracket A3 B. Okay, and well, you have, so let me put bracket here, and you get another term dx1, dx2, dx3 trace have, let's say 1, 3. So probably then you get minus A2 BV, right? So you just expand in components and plus a few other terms, right? And then for the first term, what you do is you consider, so because this is f1, 2, and then you consider this dx1, dx2 to integrate this f1, 2, then you replace as a holonomy around the bracket determined by 1 and 2. And then this dx3 is integrating this Poisson bracket. Yeah, it's integrating this Poisson bracket dx3, A3. Yeah. So here, then it is f1, 3. So here you are just going to take dx1, dx3 to integrate this f1, 3, and then take dx2 to integrate this Poisson bracket of A2. Yeah.
So I have a question here.
Okay.
Can you assume that F12 is independent of X3?
F12 is integral, no.
Is independent of X3? Independent.
So why? So you see here. So I want to replace F by holonomy, right? Components of F of holonomy. So here the holonomy around the bracket spanned by I and j, it equals to dxi dj fij.
Oh. Okay. Let me see.
Okay, so this is just this is just component of F. So component F, you assume, so here probably I should mention. So the discretization is that you assume this Fij, although this is a field, it is a function, but it's approximately a constant along this surface.
Oh, okay, got it.
Yeah, you can view this is just some kind of coordinate area times times this F.
Okay.
Well, this helpful. It's not very much necessary. Not very much necessary, because here you are anyway split up this integral dx1. So you are just integrating dx1, dx2.
Yeah. I mean, what F12 is independent of?
Yeah, F12 definitely. F12 in principle depend on x3.
Yeah.
Okay.
Okay, you are.
I see your question. I see your question. So F12, yes, indeed. In principle, F12 depends